Hello and welcome to the Lava Academy podcast, your monthly dive into the world of volcanoes, lava, and the forces that shape our planet. We're a team of lava enthusiasts based in Reykjavik, Iceland, part of the crew behind Lava Show, the world's first live lava show, where we remelt real lava and pour it out in front of a live audience. But this podcast is where we go deeper into the science, the stories, and the people behind the eruptions. Each month we'll bring you the latest volcano news along with conversations with a range of guests from leading geologists and volcanologists to locals who've witnessed eruptions up close. We'll cover everything from the science of how volcanoes work and the tectonic forces shaping Iceland to the ongoing activity on the Reykjanes Peninsula, historic eruptions, and the ways in which volcanic events impact people and communities. Whether you're a curious listener, a science enthusiast, or someone who just thinks lava is cool, and it is, then this is the podcast for you. So welcome back to the Lava Academy podcast. I am your host, Iain MacKinnon, a former primary school teacher from Scotland, now living in Reykjavik and playing with lava for a living. Yay! And I am joined by my co-host, Ragnhildur, Ágústsdóttir.
Very happy to be here.
Indeed, and we're very happy to have her.
No.
Aw, shucks. I have to say that. She's my boss.
Well, you better.
We're also very happy to have our fantastic guests with us this month. So we actually got two of them. So let's just jump over to that interview right now. All right, so we're joined today by our special guests. We've got Philip Ringrose, who is a professor in energy transition geoscience at the Norwegian University of Science and Technology in Trondheim. Whew, what a mouthful. And Chloé Delbé, a PhD student who's working in CO₂ detection over volcanoes. We'll come to Chloé in a bit, but we're going to start with you, Philip. So tell us a little bit about yourself, your background, and what does he actually do?
That's a good question. Well, funnily enough, I was brought up in India, of all places.
Right.
And when I was a child, I saw the huge Deccan basalt plateaus. And I like to think that inspired me to become a geologist. Anyway, I moved back to Scotland where I did my education and became a geologist. Uh-huh. And then, for a while in the UK, I got a job in Norway. And I sort of was an economic migrant. I moved to Edinburgh. I moved from Edinburgh to Trondheim. And I've been there now nearly 30 years. So I'm pretty much domiciled Norwegian now.
Yeah. And so, yeah, in terms of what you're actually doing then, what does your work entail, broadly speaking?
Well, as you said, I'm a professor of energy transition geoscience. Well, I like geology and geophysics, which is what our group work with. But the hot topic these days is what should these geologists and geophysicists be doing in the energy transition? Mm-hmm. Because in the last several decades, a lot of geoscientists have worked in some way supporting oil and gas activities, finding where the oil and gas is. And they've had a great career doing basic science in support of the quest for oil and gas. But nobody wants oil and gas anymore for good reasons. Uh-huh. So then the question is, well, what are these next generation of geoscientists going to be doing? And they're going to be placing wind farms, developing geothermal energy, and storing emissions from our industrial society underground. And it's the storing emissions underground that's my special topic.
All right. So we're based at the Lava Show, and scientists like yourself, you seem to be pretty excited about lava, generally speaking. Why is that? What is so interesting and exciting about lava from a scientific point of view?
It's a really good question because I am not a volcanologist, right? Uh-huh. But I'm just so inspired by the Lava Show, by understanding basalt pouring down a mountain and the process of that basalt cooling to form a lava. Now, why would I be so interested? Well, it is a fun thing to watch, obviously. But for me, lava in many ways, or basalt, is the beginning of everything on Earth. Because I work with other kind of rocks, sedimentary rocks, understanding where oil and gas reservoirs are, and now where we would store CO₂, in rock formations which are in the sedimentary basins. What's the connection? Those little grains of sand started off in a volcano somewhere.
Yeah.
So in a way, lava is the beginning of everything.
It all comes back to lava.
Well, we love that. You know, you say it again if you want.
I'll say it several times, but in a way, it is an inspirational thing. It's the rock type that leads to other things.
Right.
Yeah.
Now, over the history of the Earth, those volcanic eruptions led to our continental crusts where we all live, and we're very interested in the offshore basins, which are, well, actually also covered with basalts. If you were to go to the bottom of the sea, you'd find that 70% of the world's oceans have lava at the bottom.
Yeah.
So basically, lava is a very big thing on planet Earth.
Yeah.
It is indeed.
For you personally, you're a gas guy.
Yep.
So we tend to focus on the kind of lava side of eruptions. We've done these podcasts. We've been talking a lot about lava, but the gases are also a hugely important part of these eruptions. So what kind of gases are we actually talking about when it comes to kind of volcanic eruptions?
Well, maybe Chloe can help me later, but I'll start off by saying, yeah, when an eruption happens, obviously the lava comes out, but a lot of associated gases come with that. And the dominant gases are sulfur dioxide, water, and CO2. And the reason why we're interested in CO2 is there's two types of CO2 on Earth, naturally sourced CO2 and man-made CO2 emissions. Now, our society is very occupied with CO2 emissions to the atmosphere, which is the principal driver of global warming. So we absolutely need to do something about CO2 emissions. But in that process of understanding human emissions, we realize we need to understand natural emissions, volcanic emissions, and biological emissions. And that's basically why we're here in Iceland.
Yeah.
We want to understand volcanic CO2.
Right. Because for me, like, when we are posting, as an example, when a new eruption starts in Iceland or elsewhere, but I mean, we are covering a lot of the eruptions that happen in Iceland on our social media platforms and other mediums. Without failure, every time something begins, someone comments like, oh, here we go again, yet another volcano that's gonna like drown us, and like the earth is failing, and it's like all very doomsday-ish. So basically, how is it in terms of CO2? I mean, how much actually comes from volcanoes and how much is man-made?
Right. And that's a really hard question to answer. We've got a sort of first estimate of that from other previous work, but we're trying to work on that number.
Okay.
But the first estimate is that all of the world's volcanoes each year throw about 300 million tons of CO2 into the atmosphere. Now, that is a big number. And if you can imagine those eruptions going on in Iceland, Hawaii, and other parts of the world, there's an enormous amount of gas coming out. So we agree it's a big amount of gas.
Not insubstantial amount of gas.
Not insubstantial amount of gas.
Right.
So then you could think, well, oh, that's terrible. Well, it's still a tiny fraction of what humans are emitting each year. So humans are emitting what we say 40 gigatons. So that's 40,000 million tons of CO2. Okay? So all of the world's volcanic emissions is less than 1% of human emissions. And that is a mind-blowing fact, because if those huge volcanic eruptions are so apparently catastrophic, as you would say, we, the human civilization, are behaving in a catastrophic way.
Yeah, we're disastrous.
We're disastrous, So this is actually quite inspiring. And here in Iceland, there is a local discussion about CO2 emissions from geothermal power plants, because geothermal power plants, in a way, kind of accelerate the volcanic emissions because they're tapping into a natural system. But really, that is tiny compared to human emissions by combustion of mainly fossil fuels.
Right. So basically, what volcanoes are doing, whether it's directly by erupting or even just emitting CO2, is just a fraction.
It is a fraction. But it's a very important fraction because it tells us how that CO2 is behaving. So we really want to learn from it.
Yeah. And that's been going on forever and ever and ever.
It has, And in geological history, we have had global warming events, nothing to do with humans, to do with that volcanic system. So volcanoes could do something terrible on Earth, but that's highly unlikely right now. And what's happening right now is humans are doing something pretty catastrophic.
Right. Okay.
I find when I'm hosting the actual lava show that we do here, I quite often get questions related to the effect that volcanoes are actually having on the climate, because we know that they kind of have a cooling effect in the sense that if they're spewing out ash and stuff, blocking out sunlight, that's kind of having a cooling effect. But then they're also warming it with the CO2 emissions. Which is it?
It's dominantly the cooling effect, actually.
Yeah.
So if you look at the history when we've had good measurement of CO2 emissions and volcanic emissions, when there's a major volcanic eruption, it cools the Earth for 6 months to 2 years, depending on the size of the volcanic eruption. And that's due to sulfur particles and dust particles in the atmosphere causing our summers to cool down. So it could be catastrophic and it could cool the Earth. And famous volcanic eruptions in human history have caused famines by causing failure
And
of crops.
in Icelandic history.
And in Icelandic history.
Yeah.
So,
and we talk about them to some extent in the show, yeah.
right,
But,
you do, exactly. You've got lots of good examples in the show. But it is important to realize that even those catastrophic events, they only last a couple of years or 3 years at the absolute most, and then the Earth recovers. But the Earth is not going to recover so fast to human emissions.
Yeah.
That's going to take longer. So that's also a good lesson we can get from volcanoes.
Right. Wow.
So,
Interesting.
unless you are a particularly keen conspiracy theorist, then it's pretty well established that all this CO2 is not a good thing for the planet. Your big thing is CO2 storage. This may be a completely new concept to a lot of people who are listening to this. So just broad overview, what does underground CO2 storage actually mean?
So basically it's taking CO2 emissions from human activities and capturing them and putting them safely underground. And we've been doing it for actually 50 years already. So we know how to do it and we just need to speed up the process. And there is skepticism about it because some people think it'll be a new, costly industry. But I try to emphasize it's actually not new because Mother Earth's been doing it for millions of years. All we're doing is taking the hydrocarbons that were combusted into the atmosphere, capturing the CO2 and putting the CO2 back where it should be. Okay, so it's actually it's like a deposit bottle process. You're just taking the bad stuff and putting it back where it should be.
Yeah.
So it's easy. It's not easy to do. It's very plausible to do it, and it's a very important climate action. And the other thing that's maybe often in opposition to carbon capture and storage is people say, well, I just want clean energy, just that lovely green clean energy like hydropower, wind power, solar power. And we say, yeah, absolutely. We all want that. The problem is we're not going to get it fast enough. And we continue to burn coal, oil, and gas, and other industrial processes make CO2. And we've got to stop doing that. So carbon capture and storage is the way of fixing the problem over the next decades. Get those emissions back underground.
Yeah, until we stop.
Until we stop. And eventually, after a few decades, we won't be needing so much carbon capture and storage.
Right.
But we're talking about a whole generation before we won't be needing it.
Okay, so how does lava and like volcanic environments tap into this storage?
Now, this is getting where we're just studying right now. But our question is, if we put that CO2 underground, could it bubble up along a fault? Could it leak sometime in the future? Because we have to show our publics and our we say stakeholders, industry and governments who are going to support these projects that it's safe.
Right.
I think it's safe, but we have to show it's safe. So that's why we're studying what's the rate of leakage of CO2 up natural systems, and can that tell us something about the rate or non-rate of leakage in our safe stores?
Okay.
So, volcanic rocks and CO2, are they naturally interacting within the environment? Is the planet able to kind of suck stuff back in itself, or is it something that we have to kind of introduce them together?
Absolutely. We must remind all of our listeners that in Iceland, they're capturing the CO2 in basalts. So basalts is a rock type that very easily takes up CO2. And other sort of volcanic rock types called ultramafic rocks, they're also very good at that. So there's a whole class of rocks that are good at sucking up CO2.
Okay.
So that's an important place where lava has to come in.
Okay.
But they have to meet up
Yeah, but
in some way.
you're basically looking for ways of the Earth taking up CO2 that we're emitting to atmosphere. One way is to get the basalts to do it chemically, and another way is to put it in these rock formations which have huge capacity for storing our CO2.
Can I circle back a little bit? Like you said that basalt and a few other types of rocks are really good at this. Why is that? Why are they so good at this? Why are they better than other types of rocks?
They're chemically reactive.
That's that. Okay.
That's basically it. They react. If you introduce CO2 to a basalt, it naturally wants to turn into some carbonate minerals, which are promoted by the basalts. Whereas if you put CO2 into a sandstone, which is what we do offshore Norway, the sandstone's non-reactive, and the CO2 basically stays in the holes in the rock.
Right.
So that's the big difference.
Okay.
Huh.
Yeah. And
Interesting.
so the geology of Iceland, is it kind of uniquely suitable for carbon storage, or especially suitable, or, can you do this basically worldwide? Can you export this idea, basically?
You certainly can. There's a bunch of people in Iceland that are trying to export the idea. There was initially some skepticism about how fast basalts could take up CO2, but it's been demonstrated in Iceland and it works. So then the question is, could others pick it up? And so far I can think of 3 other projects around the world that are doing it, as well as the Iceland projects in basalts.
What is it that's reacting with what? Like what's actually happening? If you go a little bit more
Yeah,
in depth
yeah,
into the
yeah.
science here.
Well, one way to think about it is if you fracture a rock, this crack, it fills quite quickly with a white mineral called calcium carbonate. And that's the main one. There are others. And as geologists, when we look at cracks in rocks over geological time, they're always filled with this mineral. Okay.
Right.
So what happens in the earth is that when a crack forms, it tends to fill with a mineral. And now basalts are full of holes and cracks and fissures. And the same thing is happening. And when we inject CO2 and water into a basalt, we're trying to accelerate that process and get more of those minerals precipitated in the cracks. And the guys here in Iceland have demonstrated that they can do that in real rocks.
So that's in the Carfix project.
That's the Carfix project,
yeah.
absolutely.
Exactly. Exactly. Okay. Interesting.
So once that CO2 is down there, I mean, you were saying potential for leakage. So can it escape back out? Is it relatively difficult for it to get back out? What would have to happen for
Right.
that CO2 to get back where it was?
Well, it is a question many are asking. But to frame it, we are doing research to try and quantify how fast CO2 can move up faults, okay? And we don't have the answer right now. But there's a famous fault in Utah in mid of US, which I say is the most leaky CO2 fault on Earth, okay? Geologists have quantified how fast that fault is leaking CO2, and that CO2 is coming from a deep volcanic system. So it's not a man-made thing, it's a natural thing. And that leaky fault is leaking at about the rate of 100 Norwegians. Okay, so if you take 100 Norwegians, what is their annual emissions? It's one leaky fault in Utah. Okay, which tells you that even though it's bubbling CO2, it's not very much compared to human emissions.
Right.
Okay.
Yeah.
Right.
And the other thing is it's a tourist spot. So if you want to go and see this leaky fault, you can just stand by it and look at it and see the CO2 bubbling out. So even if CO2 did leak up a fault, it's not very dangerous and the rates are not very high. But I don't want to be over complacent because we wouldn't want that to happen at all. So what we do in our geological stores is try and make sure that we really understand that the faults will not leak.
Okay. I mean, but here in Iceland, we are sort of known that basalt is sort of the majority of our landscapes. Like, it's more than what it is on average elsewhere in the world. But how easy would it then, given that this is the process that you're researching and it seems to be working pretty well with basalt especially, like how easy is it to then, basically export this idea to almost all countries in the world? Like, is there anything really preventing it?
No, absolutely not. And I think we're learning all the time as human civilization. And when you come to a place like Iceland, CO2 is naturally bubbling up certain vents and faults and volcanoes. Okay, so we want to understand those natural bubbling processes. And for big eruptions, it's quite a lot of CO2.
Yeah.
Okay, but that learning that natural volcanic process is going to be really important for, as you say, exporting the idea around the world, because what we're trying to say is that putting CO2 underground is not a dangerous thing to do. It's a good thing to do. It's how we save our atmosphere from too much CO2, which is leading to global warming. Whereas there's a lot of skepticism in many countries. Germany is a classic one. They don't want any CO2 storage in their backyard. Why? Because they have a false impression of the risks. So we're trying to explain that CO2 storage is not only a good thing, it's a very safe thing. But that's not an argument we've won yet.
No,
We have to
Yeah.
do more work to explain that this is a very safe thing to do.
So what are the misconceptions that they have? Like, what would be an idea of something that they claim is a risk of doing this that, hasn't really been proven or disproven?
Right.
yet?
Well, one of the campaign sort of street campaigners would show a bomb exploding of CO2, but CO2 doesn't explode. Okay.
Okay.
So in our society, we burn a lot of methane, natural gas, for our energy systems.
Yeah.
Methane is an explosive substance, and yet our society is very used to handling it. CO2 is a non-explosive substance, so it's not nearly as risky as methane.
Mhm.
And we do know how to handle CO2. We know how to put it in a pipe and inject it in a well and put it down there. So basically, I would try and argue that CO2 is much less risky than some of the activities we already are familiar with.
Right.
But these misconceptions are somehow that CO2 is a dangerous thing.
Yeah.
Okay.
There's only very specific situations where CO2 is dangerous, and that's accumulation of CO2 in a sort of low place.
Yeah, like
So
a valley or
like
something.
a valley, and that would cause suffocation. So I'm not saying there's no risk, but the risks compared to other human activities are very low.
Yeah, because I can imagine as well, I mean, coming from the UK and, maybe folks who come from the States who heard a lot of, for example, talk about fracking for oil
Yeah.
and the dangers involved with that. I can see that people might equate the two things because you are pumping a substance down below ground. That's how they're doing with the fracking for oil, like pushing high pressure liquid down these cracks and squeezing out
Yes.
all that oil. Do you think people have kind of got that idea that's
They definitely have. You've hit another sensitive button because
Yeah.
CO2 storage is very polluted by association with fracking for gas.
Yeah.
And so the experts in CO2 storage have to work hard to say, no, that's not what we're trying to do.
Yeah.
We're putting it in safe rock formations that absorb and take the flow very easily. We're not fracking anything. We're just pushing the CO2 into permeable rock formations. But in the public mind, they could be well associated with each other. So that's another problem we have. Yeah.
Yeah.
Yeah, I mean, we're all about like trying to get the word out there, what has actually been scientifically proven and whatnot, in terms of anything that has to do with geology. But I think it's interesting that, in this, just as in everything else, there are these misconceptions.
Yeah. And facts matter. And it's really
do.
just explaining what's happening.
Yeah.
Yeah,
And
exactly.
we find, like, even through doing this podcast, it's quite interesting and quite revealing when we're having guests on to find out the misconceptions that people are coming across in just in their day-to-day work related to whatever their topic is, like this. So it's interesting. So I mean, that's what you've just been saying. That's providing a massive challenge to actually getting this out on a wider scale. There's I guess you would call it a political challenge.
Yep.
But there are also probably technical challenges involved in that as well.
Yeah, I wouldn't underestimate the technical challenges. We've just built 2 CO2 transport ships in Norway, and they're gone into operation. So we've learned how to put compressed CO2 into a ship and transport it from place A to place B, capture site to storage site. And that involved lots of learnings. And the scaled-up storage project in Iceland called Carbfix, they're now looking to similar technologies. Could they take ships of CO2 from Europe and store it in
Bring it here,
Iceland?
yeah.
So, that's great. And that's a kind of, technology transfer we want to happen. But it's not that it's easy. You have to get the pressure, the temperature right, and understand the composition of the CO2 in the ship and have good offloading and onloading procedures. So, that's techie and it's possible, but we're demonstrating you can do it right now, which is fun.
But I mean, for me, I'm like a little bit like, I feel like it sounds very much like we're already doing it, but it's still being researched. We still don't know all the facts and all that. I mean, on what scale could we actually do this? Like, could this solve our climate crisis, or
Super question, super question. Well, there are more than one answer to that question, but my balanced answer from climate science analysis is that carbon capture and storage has to do about a fifth, maybe a sixth of the global lifting problem. Okay. So it has to take a lot of our emissions and put them underground, but not all. We're going to do the biggest share of cutting emissions by renewable power and energy efficiency. So, for example, when you buy your electric car, you are improving the efficiency of transport, and hopefully you're using green electricity to run your car. But you're always also in total using less energy because a petrol engine is less efficient. Okay. So you can think about that through the whole of human activities. There are many industries where you can become more efficient and burn less, but ultimately you have to burn something for energy. We make coal, steel, cement, many manufactured products in the petrochemicals industry and the chemical industry. All of these need energy. And it's those hard to solve problems that are tackled by carbon capture.
Yeah.
Because we take those emissions that we really can't get rid of in any other way and put it underground. Another good example is fertilizer. I mean, the world needs food. When you produce fertilizer, there's a huge CO₂ emission. It's a very easy emission to capture. We should just be getting on with it. But unfortunately, we're a bit slow.
Maybe, sorry, for me, I find this very fascinating. But, when it comes to doing something like this, it always, no matter how sad it is to say it out loud, it always comes down to money.
It does.
So how expensive is this methodology?
At the moment, carbon capture and storage, say at full scale, is about $200 per ton. Okay.
Okay, I have no idea if that is a lot or very little.
So if you think of it back to the average Norwegian or the average Icelander, the average Norwegian is emitting 6 tons per year. So the cost of capturing all the Norwegians' emissions is 6 times 200, $1,200, or say euros. Okay. That's not a lot compared to your personal tax bill to the government. Okay. No. And then I've got another...
Especially in Iceland.
Especially in Iceland, right? So, people think that's a lot of money. But as I explained, that's not a lot compared to other activities.
No.
So in Norway, we've got the world's best take-up of electric cars because of government incentives. So we now have 90% of new car sales being electric in Norway. And that's because of a government incentive system, which is more like $1,200 per ton.
Yeah.
Okay. So our society is more than happy to subsidize electric cars to a high price. But when they see the price for carbon capture and storage, they say, oh, we don't want to spend that money.
Yeah.
What's it in it for me? What is in it? Yeah, right.
It's the not seeing the immediate personal benefit.
Exactly.
Well, this is very interesting. I hope someone in the political field is listening.
So do I. The numbers are all up there. So I would say carbon capture is expensive, but as an action to save the climate, it's not that expensive.
Yeah. It's maybe way cheaper than many of the alternatives.
Absolutely. And don't let me give you the impression that I don't want solar power and wind power and other renewables.
No.
They can become very cheap, and we definitely want them. But the point is the carbon capture is there for the other hard stuff.
Right. Exactly.
So this lava-based carbon storage, do you see that as a bridge to get to a certain point, or do you think that is in itself a kind of permanent part of the wider strategy going forwards?
Certainly the Iceland pioneers of carbon capture and storage, they would like to see their technology taken up by many other parts of the world, especially parts of the world that don't have better formations for storing CO₂. So there will be maybe dozens of countries which are using basalt, but for capturing and storing CO₂. But I think that the world's sedimentary basins will take the lion's share of it.
Okay.
Because in the Sleipner project offshore Norway, we've stored 20 million tons of CO₂ in a little patch that's only 5 kilometers across. Okay.
Wow.
So that's a lot of storage per square kilometer.
Yeah.
Whereas for the basalt storage, you'll need quite a lot of volume of basalt and water to get the same volume of storage. So in total, I would say basalts will be very important, especially in some countries like Iceland, India maybe. But the storage in permeable rock formations will be even bigger, or should be.
So what is responsible for that discrepancy between the two, between the basaltic versus those kind of sedimentary beds that you were talking about there? What gives them greater capacity than
it's kind of like how many holes are in the rock.
Right.
You know, a sandstone has
like a
about
porosity
30%
issue.
porosity.
Yeah.
And a basalt, I don't know the number, but I would say it's a few percent porosity. And then you're relying on the water percolating through the cracks. So, you know, it's something like that. But we're learning all the time. And, you know, some expert on basalt storage might tell me, it's better than that.
Yeah. No, that's it. I find this all super interesting. I thought I knew some, but clearly not enough.
Well, we're all learning, right?
Yeah, we're all
That's
learning.
it.
True.
So, I mean, we were talking about misconceptions and stuff. If there was one thing in particular that you wished that the general public understood either about volcanoes and climate change or about carbon storage, what would that one thing be?
I'm only allowed to pick one.
You can go more than one if you like. Feel free.
You know, I think the biggest question is that the world needs to understand we need carbon capture and storage to reach the 2-degree warming scenario.
Yeah.
If we don't do it, we really have a big problem. So I always say I like renewables as much as they can give me, and some countries renewable power, but we're going to need carbon capture and storage. Don't stop it. Need to accelerate it.
Yeah.
So that's the big picture. But in my field, the biggest thing is back to this risk of storage.
Mm-hmm.
We're trying to, you know, allay the fears that CO2 storage is risky by showing that when you put the CO2 underground, it stays there. It's actually very hard for the CO2 to percolate to the surface. It keeps on getting bonded by chemical processes and physical processes, and it finds it very hard to get to the top. But as scientists, we have to demonstrate that. Yeah. And that's really where Chloé's research comes in. She's trying to understand the link between tectonic faults and CO2 emissions or natural flow processes.
Right.
Okay, well, on that note, then let's just head over to Chloé. Hi there, Chloé.
Hi.
So just, again, give us a little overview about yourself and just who you are and what is it exactly that you're doing.
Well, I'm from France. Less exotic, I guess, than India.
Or Scotland.
Or Scotland, yeah. I started my PhD a year ago at the Norwegian University of Science and Technology. And so my PhD is not only about CO2 detection over volcanoes. It's mainly what Philip talked about. It's about seeing if we can link natural CO2 emissions with the tectonic setting, and this in the North Atlantic region. So we're encompassing Iceland, but also offshore Norway. So yeah, that's what I'm trying to do.
Yeah. Were you always particularly interested in volcanoes, or did you kind of come to the volcanoes because of your interest in the other science?
It's funny because so when I was a kid, I like a lot of kids. Volcanoes are really cool.
Yep.
What are you talking about? No, I totally get that.
They are really cool. And when I was a kid, I also really liked them. I was scared of them, but I liked them very much. But then it's kind of something that I forgot about while growing up. But I was still interested in earth sciences a lot.
Yeah.
While in high school, I learned about geology, and I was very happy that, for instance, in the French examination system, we have this national exam on the last year of your high school, and I was very glad because we had geology on this exam. We could have had also biology or other things. So that was really nice. I was very happy. My brother took the same exam at the same time. He was very sad because he didn't like it, and I was over the moon. Yeah, and then I wanted to continue studying earth sciences in general during my studies, and so and I learned about carbon capture and storage during my bachelor. I think kind of during my bachelor, and. Yeah, and then I can maybe, just to explain a bit more, I'm very talkative.
That's okay, go for it.
Well, that's why you're here.
I discovered about CCSN first, about Iceland, more about Iceland, because this was a very, very, very cool way of storing CO2 underground. And then later on, as I got to do an Erasmus or choose a destination for an Erasmus, I knew about Norway. I could go to Norway, and Norway is also working on CCS. So I was interested in that. And it's during my Erasmus that I had this course lectured by Philip, and I enjoyed it very much. And I really wanted to go for a PhD. So then I came back to France, finished my master thesis, but at the same time I contacted Philip and saw if there were any positions that could be advertised about this. And then I applied to one, and here I am now around this table.
Yeah, he was actually telling us earlier that, you know, this has been a dream project of his for a long while, and so you basically came as an angel, you know, to save us all.
yeah, maybe that's a bit, yeah.
No, just say yes.
That's a bit romanticized.
We don't put you under pressure.
No.
It's a very good project.
It's a very nice project, and it's very fulfilling, let's say.
So, I mean, monitoring volcanic gases. I mean, why monitor volcanic gases? I mean, what's the point? What does it actually tell us?
That's because, as we said before, it's because volcanoes, they are large emitters of carbon dioxide. So we need them in our equation when we want to quantify those CO2 fluxes in the North Atlantic region, and especially over Iceland, because Iceland is this weirdo of geology, let's say. because
you know, the tourist board. They should come to Iceland.
Yes.
It's the weirdo of geology.
The weirdo of geology.
It's true.
It's true.
It's a lot happening here. A lot. And so, monitoring those volcanic gases will have a huge weight in such a small area, like in such a small portion of the whole area. So we need to take them into account.
Can I ask, maybe, I don't know if you know the answer to this, but I've heard, maybe slightly sidetrack, but I've heard that it differs a lot between volcanoes and volcanic systems, how much CO2 they emit. Yeah. And maybe it's an urban legend, but I've heard that Katla volcano emits a lot of CO2. Have you heard this, or do you know this? Or do you know if it's different between volcanoes?
I think Katla is the volcano in the south.
Mm-hmm.
Yes, it does emit a lot. And we were talking about this with a guest expert from IMO on Monday.
Okay.
That this one is a particular one, and they have several theories about it, which I don't remember. But it's theories, I think. It's but it depends from one volcano to another. It depends on the composition of the volcano. And then also, if you go in Iceland, it's low effusive usually, or basically calm eruptions with lava flowing.
Yeah.
In other places, it's way more explosive.
Big.
Yeah,
So,
and one thing I learned on this trip with Chloé was that some volcanoes, when they erupt, they burn a lot of vegetation at the same time.
Yes.
Yeah.
So we learned that we need to also take into account biological emissions associated with the volcanic emission.
Yeah, true. Because I mean, we've seen that a lot recently, where
On the Reykjanes
much of the
Peninsula.
problem with the air quality in the city and some of these recent eruptions was not because of the volcano itself. It's because of all the moss and stuff that was burning at the same time.
Right.
And-
And it turns out to be really important.
Yeah.
Yes. So when you're measuring CO2 coming from volcanoes, what are the methods that you use? How do you do it?
I use this novel method of satellite measurements of CO2. So we don't have a lot of satellites measuring the carbon dioxide. There's this one.
So hold on again. Pressing pause for a second here. In my head, when you're thinking, okay, you know, we're going to be checking what the gas emissions from this volcano are, I would have thought that would involve, you know, taking a physical sample of that and analyzing that sample. You're not doing that from a satellite.
No.
What is the satellite actually doing?
Oh, okay. So if I have to explain, it's
In
great.
simple terms.
It's a great question, but explaining this in simple terms is very, very hard. Let's see how I can do this. The sun.
It's that challenge for you.
The sun emits light. This
Yep.
light is then
With you so far.
this light goes through different layers in the atmosphere
Right.
and then is reflected by the different molecules that are constituting the atmosphere.
Yep.
And CO₂ is one of them molecules, but molecules, they will absorb part of the sunlight and will emit some of it. And those little fraction of CO₂ that is re-emitted, of light
Kind of
that
bounce
is
back,
re-emitted, that
effective-
bounces back.
Yeah.
They have different wavelengths.
Wavelengths. Yeah.
Mm.
So light is a spectrum,
Mhm.
and on the spectrum, CO₂ will emit in mainly two little bands that
Mhm.
are in the infrared, in the infrared, which is not visible for us.
Mhm.
And this is what the satellite will measure.
Okay.
Okay.
Basically.
So it's picking up what's being reflected back from those CO₂
From the
particles
CO₂
in the atmosphere.
Exactly. Yeah.
So if you've got a higher concentration of CO₂, you're going to get more stuff bounced back up to the satellite.
Yeah.
If there's less CO₂, there's less.
Yeah, and this is how you discriminate between different molecules as well, because each molecule will re-emit different.
So the
wavelengths.
area of the electromagnetic spectrum
Yeah,
that's being bounced back is what's telling you what actual gas that is.
the position on that spectrum will tell you which molecule it is. And for some molecule, it's easier than other, because some have a larger.
None of this sounds easy.
No, it all sounds very complicated.
Yeah. The detection threshold of the satellite, which is the orbiting carbon observatory, that was launched by NASA, has a detection threshold of 1 part per million. I don't know if people are familiar with 1 part per million. If I take 1 million molecule, it's one molecule out of
Within those million.
within
Yep.
those million
Oh,
that is,
wow.
or maybe particle that
Mhm.
are that is CO₂.
Okay.
That's serious needle in a haystack stuff,
Yeah,
exactly.
basically.
it's quite good,
Wow.
and it's getting lower and lower as they are doing some improvements on the satellite.
So it's becoming more accurate.
Yeah.
Okay.
Cool. So the information that you're getting from all of this, I mean, we've been talking about all of this kind of within a climate science point of view, but in terms of actually, monitoring and detecting volcanic eruptions, is it helpful for this as well?
Yeah, it is. It's useful for detecting volcanic eruptions. It will not forecast the eruption of
No.
a volcano. That is not possible.
No. Oh, you know.
Won't-
we're always trying to get the word out there that you
Yeah.
cannot
You
really
just can't
predict.
do that. Yeah.
It would be nice.
It
but
would be. It'd be great.
Also, when it stops, that would also be nice
That
to
would
know.
also
be nice to know.
Yeah.
But it can give you the amount of CO₂ that is emitted by the volcano, and this satellite has been used in other places around the world for volcanic eruptions. It's been used on the Chloé volcanic eruption in 2018, I think, and there's another one, the Yasur volcano, where it has been used as well.
Yeah.
So
It's kind of giving you a heads up as to if there is increased activity going on down there. There might not be anything necessarily visible at the surface. You might not even be getting the quakes that we commonly associate with volcanic activity. But if you see a big increase in the CO₂ above a particular volcano, is that kind of showing you, hey, something maybe worth watching here?
but that is before the eruption.
Yeah.
So that the satellite will probably not detect
Ah,
it
okay.
because you need.
You would have to be in place already
you-
on that spot. Yeah.
And the thing is the gases
Yeah.
are in before the eruption are too little
Yeah.
It's too few
Okay.
to be measured.
It's not until the volcano actually starts erupting that the gases
Yeah.
really
Yeah.
get released. Hmm.
That's what I
But
think
if
is.
it could be for example, useful if you want to know where the gas cloud is going.
Yes.
So when
Yeah.
because the signal is very determined by the wind direction. So if you can see where the plume is going, the plume of CO₂ gas, that could be useful information.
And this just reminds me, we do have a web page here in Iceland. I mean, now we've had these volcanic eruptions repeatedly on the Reykjanes Peninsula. And while there's not been any imminent danger to the capital area, there has been gas pollution.
There has been, yeah.
And we have this particular website. Of course, now I can't recall the exact URL, but it basically
We'll put it in the show
you,
notes. We can add it.
Yeah. But it basically shows you like where is the gas likely to be going over the next, like the span of the next 36, 48 hours, something like that. So for people who are maybe sensitive or have respiratory diseases or something, they can actually take action and try and not be in a location where they might sense it. And do you know if the satellite images about the CO₂ are used in this? Do you know?
Not yet.
They're not used. No,
They're not used.
But if you have to use a satellite to monitor the sulfur dioxide plume, they are gonna probably use the Tropomi satellite. That is a European satellite. This one, and this one has a very good coverage over the globe.
Okay.
So yeah. There's this nice web page where they have all the available satellites with open source satellites.
So people can literally just go in there and take a look.
And take a look there. And especially for the Tropomi satellite, it's really nice because it's a global visualizer, online global visualizer. So if you're curious about one volcanic eruption and if you want to see if the Tropomi satellite has detected it, then you can just go there, choose the date of the eruption, choose the Tropomi satellite, and then you will see the volcanic plume of sulfur dioxide.
I think it's so cool that they're actually just keeping this open to the public, so anyone can go
and it's part of what's happening in our world. There'll be more and more information available. And a lot of the satellites has been federally funded or by the European Union, by the United States and other countries. So a lot of this data is publicly available. And, connecting it to human health and society, that's really important because you want to be able to say, well, I want to know if my home is in a bad place or a good place.
Yeah.
And in many ways, the more that we have sort of global data available, the better our society will become because we will know how to respond. So rather than looking at extreme events all the time, you should say, okay, how do I know if my drinking water is good? Do I know if I'm in an earthquake area? So this is positive sharing of information in a way. It can be tricky to interpret the information.
Sure.
So we do need experts to help guide ordinary people how you use this data. But I think we're entering a period in our human society where there'll be more information available to everybody, which is exciting.
Speaking like a true scientist.
Exactly.
All right. Well, we have taken quite a long time over this, so we should probably wrap this up. Can I just ask you, for you personally, what is the most exciting part of your research? What is it that really kind of gets you fired up?
Volcanoes.
Correct
I'm
answer.
so shocked.
Shocker. No, I was not expecting to work that much on volcanoes throughout my PhD. If I talked to myself a few years back or a year and a half ago and say, you would be today, this day you're gonna be sitting around a table and talk about volcanic eruptions and satellites in Iceland, I would not believe myself. But it's great. It's a great turn of events. I really enjoyed very much. But it's and I really appreciate that I have been given that opportunity to also move in that direction.
Yeah.
So I think volcanoes.
Yay! Yay for volcanoes.
Yeah. Well, we're really happy that you happen to be in this position and being here with us today.
Yeah.
So.
Thank you so much, both of you. Philip, Chloé, thank you for coming along. And all the best with all of your work.
Thank you
Thank
for inviting us.
Thank you for inviting us. Yeah.
Thank you.
So massive thanks to Philip and to Chloe for joining us for that. That was a really interesting discussion. And I tell you, a lot of stuff in there I had no idea about.
No, that's what I always think before something happens, before we have someone on here, I'm like, okay, I know a lot about this. And then, I always learn a lot.
Yeah. In this case, I went in cold. I was like, oh, I've got very little idea about anything, but it was really interesting to find out more. And actually, if you do want to find out more, I know that Philip and Chloe giving us links to some of the things that they were talking about. We're going to have all of that in the show notes. So if you check out our website, lavashow.com, and you should be able to find it under the Lava Academy tab there.
Yeah. And you can always also send us an email if you have any suggestions or good ideas. Potentially, if you want to be on the podcast,
Absolutely,
you
yeah.
can send us an email.
And
to
invite yourself.
Yeah, invite yourself. Who knows if you will be accepted?
Yes.
But
You can try.
podcast@lavashow.com is the email.
Yeah.
And of course, we're also on social media. So basically, whichever you like, if it's LinkedIn, TikTok, Instagram, Facebook, and the rest, then we are there. Yeah, we're everywhere.
And of course, don't forget to subscribe as well if you haven't already done so on all of your usual podcasting platforms. But for now, thank you very much for joining us, and we hope to see you again next time. Bye for now.